Heinrich Hertz demonstrated that, like any other wave, these electromagnetic waves can also be reflected, refracted, diffracted, and polarized. You know what reflection, refraction mean? You will get to know in the later chapters what diffraction and polarization mean. But these are qualities specific to waves. So, by demonstrating all these qualities of electromagnetic waves, he proved that electromagnetic waves are waves. Okay? So, he established the wave nature of this idea. Okay? He proved conclusively that there are waves, okay, electromagnetic waves, by doing all this. It's not just fields changing, but they also travel in space. So he proved the existence of electromagnetic waves thoroughly. Okay, and when you talk about waves, people thought, that waves require a medium to travel. But the Michelson-Morley experiment, it's one of the very famous experiments in physics. That experiment proved that light travels constantly in all directions, in all ways, in free space. So it doesn't really require a medium. So that experiment, you don't have to get into the details of the experiment, but just keep in mind that Michelson-Morley experiment proved conclusively that light does not require a medium to travel. When the mechanical waves require a medium to travel, like sound waves, when they require a medium to travel, light waves don't require a medium to travel at all. They travel in space. The other way of looking at it is that treat space itself as medium. Okay? So that's how it is. So they proved that. So light or electromagnetic waves do not require a medium to propagate. They can just propagate in vacuum. And they are waves, so they can be reflected, refracted, diffracted, polarized, just like any other waves. Okay? But you also know that if there is a wave, then it can carry energy and momentum. Right? So like you send a wave, then it goes and hits something there. Okay? It can carry energy and momentum. So likewise, the electromagnetic waves also can carry energy and momentum. So the energy density of electromagnetic waves is given like this. There are two energy densities. One is the energy density of the electric field and the energy density of the magnetic field. So it is like this. This is the energy density of the electric field. I call this as E is equal to epsilon naught E squared by 2. So this is the energy density. Probably like small uv. Okay, it's better. So this is the energy density. Of the electric field. So note that this is the same equation as you came across in the capacitor's lesson. The energy density in the capacitor was also given by this equation. So it's like that here. And then the energy density of the magnetic field is given by this. So when you say joules per meter cube, okay, this is given by V squared by 2 mu naught. Again, this you came across in and the magnetism this. Okay, so this again joules per meter cube. So this is the energy density of the magnetic field. Well, what do you know? You know that B or C, speed of light, is equal to E by B, and is also equal to 1 by root of mu naught epsilon naught. So this is for free space, okay? And if it is, this is for free space, okay? This is for free space. Energy density in free space. And clearly, if you're talking about medium, then the epsilon naught will become epsilon and mu naught will become mu. So that's the difference. Otherwise, so you also know this. C is equal to E by B is equal to 1 by mu naught epsilon naught. Okay, now let me take this UV and then in place of B, I'm going to use E by C. Okay, so this gives you B is equal to E by C. This electric field divided by C. Okay, so now UB written as B squared, say E squared by C squared into 2 mu naught, right? So that's what I've taken this value from here and substitute that here. So this is equal to E squared by what is C squared? C squared is equal to 1 by mu naught epsilon naught. So that would be 2 mu naught divided by mu naught epsilon naught. Right? So C squared is this. C squared is 1 by mu naught epsilon naught. Mu naught will cancel, this will go out. This is equal to epsilon naught E squared by 2. But what is that? It's actually this. So UB is equal to UE. So what does it mean? It says that the energy in the electromagnetic wave is shared equally by both the electric field and also the magnetic field, because I may have different equations here, but actually if we put in the values of B, then this must be equal to this. So the energy in the field, the electromagnetic waves, is shared equally by both the magnetic field and also the electric field. So if you want to calculate total energy, you take the energy in the electric field, you take the energy in the magnetic field, put them together, and that is the total energy in the wave. So I hope you are able to understand this. Okay? So this is energy in the electromagnetic wave. And there is also momentum in the electromagnetic wave. Clearly, right? If there is energy and you go hit something, then you are going to impart momentum to that body. Right? So that momentum is given by this equation, energy C. Okay? So K is equal to U by C. But U is actually UE plus UV. Okay? So it's total energy in the electromagnetic wave, and that divided by C will give you the momentum. So notice this. Sunlight falls on you. Sunlight is an electromagnetic wave, it carries energy. So the electromagnetic waves from the sun come and fall on you. So they must also impart momentum. They must push you. They must change your velocity. If you are stationary, sunlight falls on you, it's going to impart momentum. Suppose you are absorbing everything from the sunlight. Then it should give you a certain velocity. It should change your momentum because it can impart momentum on you. You absorb everything. And you can calculate it. In fact, a couple of scientists calculated it, Nichols and Hull, they calculated that. And it is found that the energy that it imparts, the sunlight imparts to you is somewhere around 7 into 10 power minus 6 Newton per meter square. So if you have a meter square area, then 7 micronewton, okay, is that is the force it exerts on that area. It's a very, very, very small force, very small force. That's why you don't feel it. But this idea, this moment, the imparting momentum aspect of it, of sunlight, is what is behind what people call as the light sail. It's like this. You make a spaceship, a spacecraft, and then you put it in space. Okay, then you use sails, like the sails on a boat. You use sails to receive light from the sun. Okay, so light from the sun falls on these sails, then it imparts momentum. So there is a change of momentum. So there is a force acting on those sails. So then it must be accelerating the spaceship, which means that you don't have to have energy. You don't have to carry fuel, but you can use sunlight itself to travel in space. So that is what they call as the light sail. Okay? So, and that comes from here, but it is very small for us, and your friction and stuff, and other forces acting on you. So sunlight doesn't make you fall. It doesn't push you down. Even though it is falling on you, it doesn't push you down. But in space, there is nothing. There is no friction, no gravity, nothing. So there is a little bit of this force acting on you, so you can be pushed. You can keep getting accelerated. So that is what I mean by this. Hope this is clear to you. Let's do example problems. The first example I take up is example 8.2. Let me read the problem first. A plane electromagnetic wave of frequency 25 megahertz travels in free space along the x direction. At a particular point in space and time, E is equal to 6.3 joules volt, 6.3 J, the J direction, volts per meter. What is B at this point? Example 8.2. So there is an electromagnetic wave. It's traveling in a particular direction. The frequency is given. Frequency is given to be 25 megahertz. So 10 to the power 6 hertz. And what else is given? At a particular point in space, in time, E is equal to 6.3 J. E vector is 6.3 in the J direction, volts per meter. So at a particular point in space, so like it's traveling here, then say just take a point there, then you have 6.3 in the y direction. Okay, this is 6.3. Okay, and this is, let's say this is y, and this is x, and this is z. Okay, let's say this is y, this is x, and this is y, and this is z. E is in the direction. So they want you to find B. So what do we know? We know that E by B is equal to C. So that gives you B is equal to E by C. So I have 6.3 here, 6.3, so divided by 3 into 10 power 8 meter per second. So that is C. So B value is going to be 2.1 into 10 power minus 8 Tesla. Okay. And the wave is along the x direction, right? The wave is traveling along x direction. This is the direction of the wave, and this is the direction of the electric field. So what must be the direction of B? Is it, this is x, this is y, and this is z. What must be the direction of B? So this is the direction, x is the direction in which this is traveling, wave is traveling. E is here, the y direction. So E cross B will give me this direction. If B was in that direction, then E cross B would have given me that direction. But the wave is traveling in the positive x direction, which means E cross B should give me this direction. So B must be in this direction, which is actually the positive z direction. So this will have, this is x direction I, this is j, okay, and this must be k, right? So this must be k Tesla. So the direction is here, B is going to be here. So E cross B will give me that. Okay. So that is 8.2. It's a very simple problem. Example 8.3. The magnetic field in a plane electromagnetic wave is given by By is equal to 2 into 10 power minus 7 Tesla sine 0.5 into 10 power 3x plus 1.5 into 10 power 11 t. Then what's the wavelength and frequency of the wave? Then write an expression for the electric field. Okay. So let me write this. So By is given to be 2 into 10 power minus 7. It is Tesla. Okay. Then I write Tesla at the end. Sine 0.5 into 10 power 3x plus 1.5 into 10 power 11 t, small t. This is Tesla. So this is in this form, kx minus omega t. That's the form. So this is k is 0.5 10 power 3 and omega is 1.5 into 10 power 11. That's the value. So this is what is given. So B is in the y direction. So B is, suppose if this is x and this is y, so B is acting in this direction. Okay. So that is at a particular point. Okay, then the wave must be traveling in the x direction. The wave is traveling in the x direction. Wave is traveling in the x direction, and y is in the B is in the y direction. The wave is traveling in this direction, and B is in this direction. Okay, so E cross B must give me this direction. So E must be somewhere here, and E cross B must give me this. Okay. Let's see. So what I'm going to have now. So what is the wavelength and frequency of the wave? So wave length is, that's easy to do. Okay? Frequency is given. So the frequency, okay, of 2 pi f or omega is equal to 1.5 into 10 power 11. So the frequency must be equal to 1.5 divided by 2 into 3.14 into 10 power 11. So that is somewhere around 'okay, so this is going to be 1.5, this is 3.14, roughly twice, right? So it's 1.1 by 4. So that will, you will get 1 by 4 point, roughly it's equal to 0.25 into 10 power 11. Okay, so that's hertz. So that is equal to 25, another 2.5 into 10 power 10 hertz. So if we do it again, like if I bring one more zero, then it's roughly equal to 25 gigahertz. So that's the frequency. Okay. So what is K? K is 2 pi by lambda. Okay, so if we want lambda, then I can find it into either this way or another way, right? So the first way is like lambda is equal to 2 pi by K. So 2 into 3.14, so divided by K value is 0.5 into 10 power 3. So this is 1 by 2, so this will become 4 and 10 power minus 3, so you get 1.56 into 10 power minus 3 meters. So somewhere around 12.56. Okay, so 10 power minus 3. So if I do that, 12.56 millimeter or 1.256 centimeter. So either way you can do it. So that's the wavelength of this wave. And the second part is write an expression for the electric field. Okay, so B is given. Then what is E? Which direction would E be? E would be, okay, this is moving in X direction. B is here. So E cross B. So E must be in this direction. E cross B should give me this direction. So this is X and this is Y and this must be Z. Okay. So E must be in the Z direction. So EZ is equal to E naught sin kx, this traveling in x direction, minus omega t. This is a formula. I need to find E naught. E naught is very easy to find because this is B naught. So E naught must be, E naught by B naught is equal to C. That gives you E naught is equal to C into B naught. So what is C? 3 into 10 power 8 meter per second. And then B naught is 2 into 10 power minus 7. So this will be 1 and this will be 660. So this will be 60 volts now. Okay, that is 60 volts. E naught, the maximum is that 60. And then the rest will be the same as the other thing, right? So EZ is equal to 60 into sine K cannot be different. So just 0.5 into 10 power 3x and plus 1.5 to 10 power 11 t. So this is what it is. The next problem 8.4, light with an energy flux of 18 watt per centimeter square falls on a non-reflecting surface at normal incidence. If the surface has an area of 20 centimeters squared, then find the average force exerted on the surface during a 30-minute time span. Okay, so what is happening here is that you have a non-reflecting surface, which means the light that falls on it will be completely absorbed. There is no reflection that is taking place. So what it means is that the wave comes with a certain speed, and then that speed becomes 0. So completely absorbed by the material. There is no reflection that is taking place. That's important. Okay, so there is an energy flux. The energy flux is actually intensity of the light. That is 18 watts per centimeter square. So intensity is given. Example 8.4. So that is the surface, and then light falls like this, normal to the surface, and all that is falling on the surface, all the light that is falling on the surface is absorbed completely. And what is the intensity of this light? The intensity of the light, in other words called as energy flux, is given as 18 watts per centimeter square. So intensity is actually power per area. So this is given. That's the amount of that's the intensity with which it's falling. And how long is it falling? It is falling for 30 minutes. The duration time is equal to 30 minutes, or 30 into 60, which is equal to 1800 seconds. So for 1800 seconds this is falling. And what is the area of the surface? It is 20 centimeters square. Okay? The area of the surface, you know, like you have to imagine this on the other side. So there is the surface is there, an area is given by 20 centimeters square. It is also equal to 20 into 10 power minus 4 meters square. So you get all the data. This is what is given. And now they want you to find the average force exerted on the surface during a 30-minute time span. What is the average force that was exerted on it? How do you find the average force? Then what is force? Force is the rate of change of momentum. So if you can find the average momentum which changed, the total momentum that changed over that time, sorry, not average momentum, the total momentum change divided by the time it has taken for this momentum to change, then you will get the force. So force is actually okay, dp by dt is momentum. Okay? So the first thing I need to do is I need to find the momentum. So momentum P is given by U by C, the amount of energy in the wave divided by the speed of the wave for complete transfer. What it means is that all the energy that is contained in the wave is totally fully absorbed. It's like the wave is traveling with some speed c, now it has become 0. Okay, the speed has become 0. So it's totally stopped. So all the energy this has been transferred to the other body. That is what it means, right? So if this is the case, then I need to find u and then divide it by c. Then what is u? U is what I need to find. So what is u? So U is equal to, well, we have got intensity, and intensity is power per area, and if I take intensity and multiply that with the area of this, then I will get the power, right? From this, if I take intensity and multiply that with the area, then I get the power. And power into time will give me the energy, total energy absorbed over a 30-minute period. So that we get. So this is equal to 18 watts per centimeter square, right? Or watts per centimeter square. Multiplied by what is the area? It's 20 centimeters square. So 20 centimeters square, and centimeter square and centimeter square will go. So you get 18 into 20 watts. That's a total. That's a power. Okay. And if you multiply that with time, time is T is 1800 seconds. So this is the total energy. Okay. So this is seconds, right? So we will get joules now. So this is going to be equal to 18 into 20. Okay, so many joules. Or you can say, 18 squared, and then you can multiply that by 2, then do that 2. So this amount of energy you get. Yeah, I got U. So what is my P? My momentum is U by C. So that is equal to 360 into 1800. So divided by, what is C? C is 3 into 10 power 8. That's meter per second. So clearly this will become 12. So I get 12 into 18 into 10 power 3 into 10 power minus 8. So that will give me 204, I suppose, right? 2.16 into 10 power minus 3, and this is MV, kilogram meter per second. So that is the momentum. I got this is the total momentum change. So they came with 7 speeds and they become 0. So this is a total momentum change. Then what is the force? The force is total momentum change divided by the time it took for this to change. So this is going to be equal to 2.16 into 10 power minus 3 divided by, what is this time? It's 1800, right? Second. 30 minutes. This is happening for 30 minutes. So this is going to be 1800 or 1.8 into 10 power 3. Okay, this will go and this will go, and this is going to give you this is 10 power 3, right? So this will be 10 power minus 3 there. So 10 power minus 6 is what I can't remove this. Sorry. So I'm going to get 2.16 by 1.8 is going to give me 1.2 into 10 power. This is minus 3, this goes up, so 10 power minus 6. So it's a very, very small amount of force. Okay, so the average force acting on that surface is given by this. So 1.2 in 10 power minus 6 Newton, 1.2 micronewton force is acting on this surface. Okay. So this is how you do this problem. They also asked another question. How will your result be modified if the surface is a perfect reflector? If the surface is a perfect reflector, so what does it mean? Light falls on the surface and gets reflected completely. So no absorption takes place. So think about it. There is a velocity with which it comes, and hits there, and then it changes direction, okay, and will travel with the same velocity. So now the momentum will be twice this, clearly, right? So it's going to be minus mv minus mv, so minus 2 mv. You may recall from your 11th standard. So if it is mv to 0, it will be 0 minus mv. But if it is mv to minus mv, then minus mv minus of minus mv will get minus 2 mv. So what the momentum that you calculate here will get doubled here. So if it gets doubled, then the force exerted on the surface will be 1.2, twice that, so 2.4 into 10 power minus 6 Newton. Okay? That's how this is done. Okay, next we will do example 8.5. So calculate the electric and magnetic fields produced by the radiation coming from a 100-watt bulb at a distance of 3 meters. Assume that the efficiency of the bulb is 2.5% and it is a point source. So you have a bulb which is going to be point source. So this is a bulb. Okay, so light is coming all directions from that. So at a distance 3 meters, at this point you calculate the electric field value and then the magnetic field value, or I should say, since it's traveling like that, so that must be E must be that E cross B must be going this way. So B must be in this direction. B must be coming like this. Okay. So E cross B. So this line, this light is going in the direction. So 3 meters from this source. So what is the electric and magnetic fields? What is E? What is E and what is B at this point? And the other information given is this. This is a 100-watt bulb with an efficiency of 2.5%. Okay, so efficiency is 2.5%, power is 100 watts. So what does it mean first? It means that if you give 100 watts to that bulb, then 2.5% of that energy would be converted into light. So that's what you mean by efficiency. The rest would go as heat, which you would not use. You would use only light. So 97.5% of this energy would go as heat, and that is why when you touch a bulb it is very hot, and only 2.5% becomes light. You are interested only in this light. So you need to see how much power is coming out of this. Obviously, from the electrical mains, the supply, the power supply, you are going to draw 100 watts per second. You will do that. But out of the 100 watts, only 2.5 watts would be converted into power. The power in the light as light. So we are focused on that. Okay. So now, what is intensity here? What is the light intensity at that point? Because 2.5 watt power is coming out, and then as you go further and further away, the intensity will come down. Okay. So the intensity at this point, intensity is given by power per area. Okay. So you are getting the same power, but if this area is smaller, then the intensity will be great. And as you come further and further and further, then the intensity of light will go down. So what's the area now? Area here if we take this, so this is coming out, the 2.5 watt is coming out, the light is coming out, and it is going in all directions. It's not all 2.5% is going there. You give 100 watts of electricity and 2.5 watts are converted into light, and that light travels in all directions. So that power is distributed over a sphere, an imaginary sphere. So whatever power is coming out is there everywhere on the surface of the sphere. So if you find intensity, then you need to take this I and divide that by the surface area of the imaginary sphere at that point. So the point is 3 meters from the center. So the intensity is actually power per area. What is power? Power is 2.5 watts, because that is how it is get. You are concerned only about the power of the light, not the electrical power. 2.5, and this would be 4 pi r square. That's equal to 2.5 divided by 4 into pi into r. It's actually 3 meter, right? So 3 meter radius, so 3 square. So if I do this, then I'll get 2.5 divided by 4 into 3.14 into 9. I think I get 0.022 watt per meter square. 0.022 watt per meter square. So my intensity is equal to 0.022 watt per meter square. So what did we say? The energy in an electromagnetic wave is shared between the electric field and the magnetic field. So half the energy would be in the electric field at that point, and half the remaining half would be in the magnetic field. So they jointly give you that energy, the total energy. So 0.022 watt per meter square is intensity. Okay? So if the energy is going to be shared between the magnetic and electric fields equally, then power will also be shared between the electric and magnetic fields equally. If power is shared between the electric and magnetic fields equally, then the intensity, which is nothing but power per area, would also be shared equally between the electric and magnetic fields. Okay? So I can say that half the power, half the intensity is due to the electric field. Okay? I'll say maybe like the electric power, electric field, okay, and the remaining half intensity is due to the magnetic power in the magnetic field. Okay. So this you know. But what is the power in the electric field? Okay. See, if you remember, we said in a unit volume, okay, and we know this. Energy per unit volume is given by half into epsilon naught to E square. This actually must be an RMS value. So this is energy per unit volume, this we know. Now what is power at that point in terms of this? And that can be given by this expression, half into epsilon naught E RMS squared into C. Okay? C is the velocity of light. It's easy. I mean, if you just fix the area, then if you say in 1 second how much volume this would cover, then this would be, you know, like the 1 meter squared and C. So that is so much volume it will cover. Okay, and so much energy would cross this. in 1 second. How much energy would cross here? Like it's going to be epsilon naught E RMS squared, that is energy per volume, into C. Why C? This is actually C into 1 into 1, and that is why it is C. That's the volume. So now this is going to be the amount of energy. Note this. This is joule per meter cube. But here, this is joule into volume. C times 1 into 1. This area. And then if you keep 1 meter, then how much would be the volume that you need to cover? It will be C. In 1 second, it will reach C distance. So that's a cuboid you can think of. So much volume. So you take this volume, you multiply that with this UE, then you get energy that has crossed this point in 1 second. Okay, think about it. So this is what you will get. Okay, so I can take this and equate it to this one, this equation. So this is PE. It's power in the electric field, that is epsilon naught half into epsilon naught E RMS squared into C is equal to half times I is 0.022. Okay, so this and this will go, and E RMS squared is equal to 0.022, so divided by epsilon naught is 8.854 into 10 power minus 12 into, this is 3 into 10 power 8. Those things come down. So then E RMS is equal to square root of this. Take the square to calculate this quantity and take the square, then I should get 2.9 volt per meter. So 2.9 volt per meter. So this is the RMS value of the electric field there. Okay. Then it is possible for you to, if you know the RMS value, then you can find the maximum value. So what would be E naught? E naught is equal to root 2 into E RMS. So it's going to be 1.414 into 2.9. So 1.4, somewhere around 4.3, 4.4, so 4.07. So you got 4.07 volt per meter. So E naught, which is actually the maximum value, EM, is 4.04 volt per meter, then E RMS is 2.9 volt per meter. So once you know this, then you can find B naught. So what is B naught? So B naught can be calculated as E naught by C, which is 4.07 by 3 into 10 power minus 10 power 8. So this will give you somewhere around 1.3 something. Okay, 1.4 into 10 power minus 8. 1.4 into 10 power minus 8 Tesla. Okay, so this is one. Or if you want to find B RMS, then simply take E RMS by C, so that is 2.9, so divided by 3 into 10 power 8, that is 2.9 by 3 by 3, approximately 1 into 10 power minus 8 Tesla. The answer is 9.6 into 10 power minus 9 Tesla, which is the same as 1 into 10 power minus 8 Tesla. So this is how you do this problem. Okay. Just think about this. This is a critical idea here in this problem. If you understand it, then the rest is easy. So this is energy per unit volume. Now I am fixing the area as 1 by 1. I am asking you how much would cross this area in 1 second. If you think about it, then that would be C, 3 × 10⁸ meters in 1 second. So much energy would cross in 1 second. That's it. So that's why you are multiplying it with C. Okay. So This is into one by one. Okay. Hope this is clear to you. Okay, the rest of the lesson is a description of the electromagnetic spectrum. And we said that if you have a charge and then if you oscillate the charge, or depending on the frequency of oscillation, you are going to have different electromagnetic waves with different frequencies. So the frequency range decides the category in which you will put an electromagnetic wave. Okay? There are basically these categories. Radio waves, and then microwaves, and then infrared waves, and then visible light, okay, and this is what you call as light, okay, visible light, and then ultraviolet, ultraviolet waves, and then X-rays, and then gamma rays. Okay, so this is the increasing order of frequency. Okay, the frequency increases as you go from here to here. So the frequency increases like that. The low frequency electromagnetic waves are called as radio waves, and then higher than those frequencies would be microwaves, and after the infrared waves and light, ultraviolet waves, X-rays and gamma rays. So this is how you classify or categorize the electromagnetic waves. But what is the difference between this, this electromagnetic wave and this wave, or any other wave in between, is simply the frequency. They are produced by the same process, in the sense that like you have a charge, then you make it go up and down, or you accelerate the charge with a certain frequency, and that charge is going to produce, this process of accelerating charges is going to produce an electromagnetic radiation. Okay? So depending on the frequency of the radiation, you are going to classify the radiation in one of these categories. It's very easy to remember this. Okay, the order R-A-M-I, use a different color now. This is R-A-M-I-L-U-X gamma. It's right. So this can be written as Ra, Mi, let's see. Okay. So the order is this: radio, microwaves, infrared, light, ultraviolet, X-rays, and Y is for gamma. So gamma looks like Y, so you say Y. So it's Rami, Luxi. So if you can remember this Rami, Luxi, then you have all these categories memorized. Just remember this Rami, Luxi: radio, micro, infra, light, ultraviolet, X-rays, and gamma rays. So if you go through your textbook, they give you the frequency ranges for all this, basically. Okay, those frequency ranges will define these classifications, and on the other side they are given you the wavelengths also. Obviously, if you know the frequency, then you can easily calculate the wavelength by using this formula: C is equal to F lambda. You know this? You know this anyway. 3 into 10 power 8, so you can find lambda. Okay? So you either know this and you can get to this, or You can know this and get to this. So one set is enough for you to know. The other set can be easily obtained from simple calculations. Okay, so that is what is given here. So generally, and after this there are only descriptions. So radio waves are basically used for transmission purposes, right? Like radios and TVs and FM stations and stuff. You can use them for communication purposes, your cell phones. So radio waves are used for that purpose, and then the frequency ranges are given here. There are, the medium waves and short waves and long waves, and all these things are there. Okay, so it depends on the frequency. And obviously, long waves will be, the frequency is small, then the lambda will be long. The frequency is high, then lambda will be small. So we have long waves, short waves, all that we have. Okay, so that is in the case of radio waves. So that is one. So microwaves you've seen, like you know the microwave ovens and stuff, and so you can you have many uses for it. For example, the speeding ticket that you get when you drive fast, there will be the policeman with a gun, a speed gun, right? So they can easily measure you at the speed with which you are going, and what you are using there in the speed gun is electromagnetic waves in the microwave frequency range. Okay, so I'll just read a couple of sentences from that paragraph. Due to their short wavelengths, they are suitable for the radar systems used in aircraft navigation. Radar also provides the basis for the speed guns used to time fast balls, tennis serves, and automobiles. That's what I said. Okay, even when you watch a cricket match, when they say that a particular bowler is bowling at say 150 km per hour, they are using the microwaves to measure the speed, just like you use radar. Okay, so that's it. It's used for that purpose. The infrared waves are actually the heat waves. Okay, third one, infrared waves are actually the heat waves. So when your mom brings hot food and then you can feel the heat. Okay, it's sitting on the table, then you can, when you touch the utensil, the plate, or when you touch the food, you can feel the heat. So the infrared waves are called as the heat waves. Okay? We perceive infrared waves as heat. We don't perceive these with our senses. Okay, our body cannot sense either radio waves or microwaves, but it can sense infrared waves, because what you feel as heat is actually infrared waves. Okay, see, why does it happen? Because your body consists of a lot of water. So water molecules can absorb these infrared waves. So the body can easily absorb the infrared waves and get heated up. Because once the water molecules absorb heat, then the electrons will go up and down, and then they start, they'll be in constant motion. The atoms will be they'll jiggle a lot inside your body. So then they will radiate energy. So you get heated up. So it's the reason why you are able to sense infrared waves as heat is because your body, or your cells in the body, have a lot of water. Okay, so that is the reason. So there are other things, like carbon dioxide and ammonia. They also absorb infrared waves, infrared radiation. Again, the reason why the global warming takes place is because of this. So you have a lot of carbon dioxide in the atmosphere. Then sunlight comes in, and what happens is outer atmosphere, it absorbs the sunlight and then it re-radiates. It's like the spectral lines you saw, right? So the electrons may get excited to a much higher level, and then when they do the jumps, they don't, the different kind of jumps will they release energy in certain quanta. Okay, so it may receive a lot of energy and then go up. So fourth or fifth level, And when the electrons jump back, they don't straight away jump, they'll jump into the third, and then second, and then first. When they do this, then the energy that you gained as one big packet is now released in small packets, and that's what you would perceive as a part of it you would perceive as heat. So that is why, like, when you have a lot of carbon dioxide in the atmosphere gets heated up, then the carbon dioxide holds the heat, and it causes ice, glaciers and other things to melt, and it causes water levels to rise in the world, and cities, and the coastal cities could submerge. Maldives are in deep trouble now. So all these things happen because of this. Okay. The next one is visible rays, that's light. So you know this, there is a certain range, you have WIBGR, right? Violet, indigo, blue, till red. So you know all this, and all these have a certain frequency ranges. Violet will have a certain frequency range, then indigo, blue, red, up till red, you have different frequency ranges in which. So these are the frequencies your eyes can sense. So infrared, your body senses as heat, and this frequency range, your body senses as light, or your eyes sense as light. Okay, so infrared and visible light, these are the things that your body can easily sense. Okay. So again, we talked about resonance and stuff, and in these frequencies, there is a certain kind of resonance that is taking place among the cells and the electrons in the eyes, and that is why this is happening. Okay. Next one, ultraviolet. So again, ultraviolet rays, UV rays can be used for water treatment, to purify water. It can kill germs and stuff, and because there's a lot of energy and stuff with much higher energy. So as the frequency increases, the energy also increases. Okay? So clearly, visible light will have much higher energy than infrared waves, and ultraviolet will have much higher energy than visible light and infrared radio waves and microwaves. Okay? As the frequency increases, the energy in the wave also increases. Okay? To come to talk about ultraviolet, I have to read this. UV light in large quantities has harmful effects on humans. Exposure to UV radiation induces the production of more melanin, causing tanning of the skin. UV radiation is absorbed by ordinary glass. Hence, one cannot get tanned or sunburned through glass windows. Welders wear special glass goggles or face masks with glass windows to protect their eyes from large amounts of UV produced by welding arcs. So the welding arcs, apart from the visible light you see, a lot of UV light is also coming, which you can't see, but it can hurt you. Due to its shorter wavelengths, UV radiations can be focused into very narrow beams for high precision applications such as LASIK eye surgery. UV lamps are used to kill germs in water purifiers. Ozone layer in the atmosphere plays a protective role, and hence its depletion by chlorofluorocarbons, CFCs, gas such as freon, is a matter of international concern. Okay? So that's about UV. The next one is X-rays. You know what X-rays are and where they are used in medical profession. They are used a lot to reveal the bone structure and other things. So there are they're produced in a certain way. Okay. So one common way to generate X-rays is to bombard a metal target by high energy electrons. X-rays are used as a diagnostic tool in medicine and as a treatment for certain forms of cancer. Because X-rays damage or destroy living tissues and organisms, care must be taken to avoid unnecessary or overexposure to X-rays. And that is why, whenever you go and take an X-ray, the guy who takes X-ray will leave the room and will just make you stand. Because you are the only one person, as far as you are concerned, who is getting the X-ray. But for him, you are one of the many people who come every day, every hour to take the X-ray. So if he is going to be there, he is going to get exposed to those X-rays and he will be suffering. And that is why he normally doesn't stay when the X-ray is taken. Okay. The next, gamma rays. The gamma rays are anything beyond X-rays, you call them as gamma rays. There's nothing, beyond gamma rays. After this frequency range, anything and everything to infinity, infinite frequency, will be called as gamma rays. Okay? They are the most powerful. So they lie in the upper frequency range of the electromagnetic spectrum and have wavelengths of from about 10 power minus 10 meters to less than 10 power minus 14 meters. This high frequency radiation is produced in nuclear reactions and also emitted by radioactive nuclei. They are used in medicine to destroy cancer cells. And then table 8.1 summarizes different types of electromagnetic waves, their production and detections. As mentioned earlier, the demarcation between different regions is not sharp and there are overlaps. Okay? Some frequency range can appear both in one category and also in the other category. So there can be overlaps. Okay? So this is about